On the following presentation, we will talk about the Kepler's planetary motion equations. Johannes Kepler was a German mathematician and astronomer very important during the 17th century. He was born on December 27, 1571, in Germany. He developed an explanation to the behavior of light in a telescope, discovered several polyhedrons, and mostly he helped vastly in the understanding of planetary motion. The first two laws were published in 1609 as an analysis of the work of the astronomer Tycho Brahe. The third law was published in 1619 in an effort to reconcile Brahe's observation with Copernicus' heliocentric solar system model.
Laws and equations formulated by Kepler in the scientific revolution are three formulas that describe the orbits of planets around the Sun. These laws contradict the accepted heliocentric theory proposed by Copernicus, in which the orbits were circular and the velocity was constant. In these three laws, the orbits of the planets are seen as elliptical, which was inferred through the study of the Martian orbit. The second and third law explain that when a planet moves closer to the Sun, it will move faster, and the distance of the planet to the Sun will determine the orbital speed. If the planet is further away, the orbital speed will be slower. Throughout the years, Kepler's planetary laws have been canonized through observations and further calculations by other scientists, one of them being Isaac Newton, who has been attributed with marrying Kepler's work with his own laws of motion and universal gravitation. This because of the comprehension that the second law proposed by Kepler is a consequence of the inverse square law of universal gravitation. So, the other Kepler's first and third laws are dependent on the square law of attraction.
As was mentioned before, the elliptical shape of the orbit of a planet is always a result of the inverse square law of gravitation, which is an ellipse. In general terms, it is defined as a set of points such that the sum of the distance from each point to the two foci is the same for all points. In this very specific case of planetary orbits, the point in the ellipse that comes closer to the Sun will be called the perihelion, and the furthest point away will be the aphelion. The focus of this first law lies in the eccentricity of a planet's orbit. This eccentricity is defined as the ratio of the distance between the major two axes and foci of an ellipse, and, by definition, this value will be 0 for a circle. The motion of any binary system is relative to the center of mass of such system. Thus, the vector distance between both masses will be r vector equal to r sub 2 minus r sub 1. Under motion in terms of reduced mass mu will be equal to m1 times m2 over m1 plus m2, which are both the masses of the objects in an orbit. The individual vector coordinates of these masses can be expressed in terms of mu, which is the first vector equal to minus mu over m1 times the vector, and the second vector will be the same but with m2. All three of Kepler's laws depend on the principle of conservation of angular momentum, which can be expressed in terms of the relative velocity and mu of a two-body system, such that the angular momentum of the system will be the sum of each individual angular momenta, which is equal to the equation that we see below. And once we do the whole development of m1 multiplied by each of the vectors will give us the cross product of the r vector times the momentum, p. Nothing specifically that v, the vector, is the average velocity, and our momentum will be mu times the average velocity. To show that the angular momentum is conserved for a member of any one binary system, we must first show that its derivative is 0, where the force of attraction is acting along the line between the two bodies. This is done by taking the time derivative of both sides of the previous equation, which, since they have the same direction, will give us 0. We can then analyze the force and angular momentum relation of the system, which can be written as the angular momentum equal to mu times the vector r cross product of the vector v, which, once simplified, will give us mu times r squared times the unit vector of r cross product by the time derivative of r. Now, we will define the acceleration of mu as a equal to the negative of gm over r squared times the unit vector of r, where m will be equal to the sum of the two masses. By taking the cross product of the acceleration and the angular momentum, we will then obtain gm times mu times the unit vector of r in its time derivative. Now, we will take the cross product of the v vector times the momentum, which will end up giving us the time derivative of gm times mu times the unit vector of r, which we can then integrate in terms of t, and we will get the cross product of the vector v with the angular momentum equal to gm times mu times the unit vector of r plus a vector constant. Now, to reintroduce the radius into the equation, we will multiply the radius vector times the cross product of the v vector and the angular momentum vector, which, once we apply some of the vector properties, will give us gm times mu r plus r times the constant c times the cosine of theta, which we can then put in the form of L squared over mu. And finally, we can assign the value of the eccentricity, which will be E, to equal c over gm mu, which is an expression from the conic section orbit. And thus, our radius will become r equal to L squared over mu squared over gm times 1 plus E cosine of theta, which can be expressed in terms of a semi-major axis A when E is in between 0 and 1. And once we equal them to each other, that is, the two r's, we'll obtain the expression for the angular momentum, which will be L equal to mu times the square root of gm times a times 1 minus e squared, which, for a bounded elliptical binary orbit, will have the center of mass at a focus in each ellipse.
Now we will discuss the second law of Kepler, the law of areas. When a planet is close to the Sun, it will move faster and will travel a longer path at a given time. The second law was discovered through the conservation of angular momentum. This law states that an object in binary orbit will cover equal areas in equal times, so the real velocity of the object will be constant. Considering the area of an elliptical orbit, we can express a given infinitesimal element of the area as di equals dr times r d theta. If we integrate with respect of r, we obtain, in terms of the rate of change in time, as the area the following equation. dA dot equals r squared over 2 times d theta dot. Then the velocity, this velocity is in the plane of the ellipse, can be divided into the sum of the radial and angular components. If we equate the angular components, we obtain the relation a dot equals r times v sub theta over 2. The angular momentum is constant, and since the radius and angular velocity are perpendicular, we obtain the relation a dot equals 1/2 of L over mu. By analyzing, we get that the rate of change of the area is the same for all parts of the orbit, which is the law of all areas that is stated as the second law of Kepler.
Now the third law, which is the law of periods, is the square of the orbital period of a planet is proportional to the cube of the length of the semi-major axis of its orbit, which is something of a conclusion to the previous two laws. We begin by integrating the rate of change of the area over time, which will give us 1/2 of L over mu times the period. We can then use the equation for the area of the ellipse, which is A equal to pi A times B, to show that the period will align with the relationship of P squared equal 4 times pi squared times A squared times B squared times mu squared over L squared. And remembering from our first law that b squared equals a squared times 1 minus e squared, we'll have an expression similar to the first law, and our period will then become p squared equals 4 times pi squared over gm times a cubed, which establishes Kepler's law of periods. This form is particularly useful for the finding of orbital periods in binary systems.
Consider the initial value problem y prime equals f of t, y in an interval of t between a and b with a boundary condition y in a equals to alpha. The separation between iterations is obtained from the division of the difference between b and a and the number of iterations n. The number of iterations states the number of times the procedure will be repeated to obtain the approximation. The new value of t, considering the spacing and the number of iterations, is the addition of the initial value of t and the product between j and h. To determine the ith approximation of the jth point, in other words, u sub I of t sub j, the initial conditions are given in the following image. W sub 10 is eta 1, W sub 20 is eta 2, and so on. To obtain the value of W sub I j plus 1, the following values have to be obtained. K1i is the product between h and the function evaluated at the initial conditions. K2i and K3i is the product between h and the function evaluated at the initial conditions. However, half of the spacing is added to the initial time, and half of the previous value obtained for kji is added to the respective initial value wij. K4i is the product of h and f evaluated in t plus h and the initial value wij plus the previously obtained kji. Finally, the ith solution at the jth point is the addition of wij plus 1/6 of k1i plus 2k2i plus 2k3i and k4i.
Now we will discuss about solving the Kepler Planetary Motion equations. To solve the Kepler Planetary Motion equations using the Runge-Kutta Method, it is necessary to obtain a system of equations which could be approximated using the method described previously. The force experimented by an object, according to Newton's second law, is given by force equals mass times acceleration. When we analyze the movement of an object whose potential energy depends only on the radial distance between both objects in the system, and which one is fixed, the field is said to be central, and the force applied on the object by another object can be obtained from the partial derivative of the potential energy of the objects with respect to the radial distance between them. So the force when an object in movement has potential energy depending only on the radial distance to a second object is F equals minus the partial derivative of the potential energy with respect of the distance between the two objects. The effective potential for gravitational attraction is defined as the addition of the centrifugal potential energy and the gravitational potential energy. The first term of the following equation corresponds to the gravitational potential energy, and the second term to the centrifugal potential energy. Both m's depend on the mass of the objects, in this case, Earth and the Sun. Now, if the partial derivative of the potential effective energy is done with respect of r, we obtain the following equation, where g is the gravitational constant, m sub p corresponds to the planet's mass, and m sub s is the Sun's mass. If we equate both equations for the force and solving for the acceleration, we obtain the next equation, where the second derivative of r with respect of t is the acceleration. Now, the first two equations to solve Kepler's planetary motion are the following. The first one is y1 prime equals y2, and y2 prime, the previous equation which was solved for the acceleration. In this system, where the field is central, the rate of change of the angle between the two position vectors and the trajectory arc is given by the next equation, where the derivative of phi with respect of time equals capital M over mu times r squared, where m is the angular momentum, mu is the reduced mass, and r squared is the distance between the two objects to the power of 2. This relation is the third equation in the system to solve the Kepler planetary motion equations.
The images that will be presented are captures of the code used to solve Kepler's planetary motion equations, with the method previously explained. The results obtained should approximate a planet's orbit, in this case, Earth's. The first image is a part of the code in which the constants model is determined. The constants used were the planet's mass, sun's mass, the gravitational constant, the initial radiant distance between the planet and the sun, the planet's initial velocity, the initial angle between two position vectors and the trajectory's arch, and the angular momentum, which is equal to the product of the initial velocity, the initial radial distance, and the planet's mass. These constants are stated at the beginning of the code because they appear in the equations to be stated next. The second model is the functions model. Here, the equations obtained through the analysis previously explained are established using the constants from the previous model. The first equation is the one where the derivative of r is the velocity. This function is f1 equals to v and depends only on the velocity. The second function is the equation obtained for the acceleration, or the derivative of the velocity with respect to time, which is equal to the angular momentum squared divided by the reduced mass squared multiplied by the radius elevated to the power of 3 plus the product of the gravitational constant, the planet's mass, and the sun's mass divided by the product of the reduced mass and the radial distance squared. This function f2 depends on the reduced mass and the radial distance. Lastly, the third equation is the derivative of the angle with respect to time, f3, and it is equal to the angular momentum divided by the product of the reduced mass and the radial distance squared. This function also depends on the radial distance and the reduced mass. This part of the code corresponds to the program. Here, it is established that the constants and functions models are used. First, the initial conditions, the parameters and values used in the Runge-Kutta method, and the result variables have to be introduced as real numbers. The number of iterations is introduced as an integer. For the solution of these functions, the case needed to calculate what would correspond to the w's of ij plus 1 are k11, k12, k13, k21, k22, k23, k31, k32, k33, k41, k42, and k43. P1 corresponds to the radial distance, P2 to the velocity, and P3 to the angle, with P10, P20, and P30 as the initial conditions of these parameters. The user is asked to introduce the time interval, the initial value of the angle, and the number of iterations to be used. The reduced mass is established to the product of the planet and the sun's masses divided by the addition of these. Also, the spacing is established to the difference between the limits of the time interval divided by the number of iterations. There is a command in which a file is opened with the status unknown. This was added in order for the values to be obtained in the procedure to be saved. But every time the code was run, the previously obtained values will be erased and the new ones will be saved. Now, the k values will be obtained from I equal to 1 to n. As seen in the image, the k's are ordered as k1j, then k2j, then k3j, and finally k4j. This was done because in k2j the values of k1j are needed, as in k3j with the values of k2j and k4j with the values of k3j. Then p1 is going to be the addition of p10 and 1/6 of k11 plus 2k21 plus 2k31 plus k41. P2 is the addition of p20 and k12 plus 2k22 plus 2k32 plus k42 divided by 6. Finally, P3 is equal to P30 plus 1/6 of K13 plus 2K23 plus 2K33 plus K43. The values of P1, P2, and P3 are then equal to P10, P20, and P30 respectively, in order for these values obtained to be used as the initial conditions in the following iterations. Finally, the third and last part of the code. Here the user asks the code to print the number of iteration and its corresponding value of P1, P2, and P3. Also, the positions in the x and y directions are determined using the values previously obtained. X is equal to the radial distance multiplied by the cosine of the angle, and y is equal to the radial distance multiplied by the sine of the angle. The end loop is closed and it is asked for the final values to be printed in the screen. Lastly, the program is ended.
To obtain an approximation of Earth's orbit, the following data was used. Earth's mass was equal to 5.97 times 10 to the 24th kilograms. The Sun's mass will be equal to 1.989 times 10 to the 30 kilograms. The initial radial distance will be equal to V0 29.290 meters times second. The initial radial distance, which is r sub 0, is equal to 149.6 times 10 to the 9th meters. Our angular momentum will be equal to m equal to pm cross r sub 0 cross v sub 0, and our initial angle was a sub 0 times o radians. The gravitational constant for Earth is equal to 6.67 times 10 to the minus 11. Our time interval in seconds is t in between 0 and 3 times 10 to the 9th, and our number of iterations was 10 to the 4th. The results obtained are gained in the following figure, and our graph is also shown on screen.
Now we will discuss an orbit approximation of a more massive Earth. To obtain the approximation of a more massive Earth's orbit, the same data as in the previous approximation was used, except the planet mass. The mass used was 1/3 more of the Earth's actual mass. The results of this approximation are presented in the black picture, where we can observe a value of the position in the x-axis, a value for the position in the y-axis, the radial distance between the two objects, the angle, and the velocity of this motion. The graph obtained from plotting the values of x and y in each iterations show the approximation of the massive Earth's elliptical orbit. Finally, we will discuss an orbit approximation with an Earth of half the Sun's mass. As in the previous approximation, the same data as in the first approximation was used: the planet mass and the time interval. The mass used was 1/2 of the mass of the Sun, and the time interval was modified to t between 0 and 21 times 10 at the power of 9. The graph obtained from the plotting the values of x and y in each iteration show the approximation of the new Earth's orbit. As in the previous approximations, we obtained the position in the x-axis, the position in the y-axis, and the radial distance between the two objects, and the angle, and finally the velocity of this movement. The graph obtained from plotting the values x and y is shown in this slide as the results of the approximation shown in the black picture.
In conclusion, we can summarize Kepler's laws of planetary motion as the following. The first law tells us that planets move in elliptical orbits around the Sun, with the Sun at one focus. The second law tells us that the area per unit time traveled by a radius vector from the Sun to a planet will be constant, and the third law says that the square of the period of a planet will be proportional to the cube of the major axis of the orbit of a planet. These three laws together neatly explain the motion of objects in a binary system, an explanation that was, in its time, entirely revolutionary and is relevant even to this day. This specific numerical method has turned out to be very practical for a stated problem, since it allows us to develop the mathematical intricacies of it in a very concise and specific manner. This way, we can better focus on the reduction of our algorithm and development of our code, which was incredibly useful. The Runge-Kutta method became a very effective method for solving initial value problems described with higher order differential equations, without the need of using the derivative of the functions. The approximations obtained gave us the expected orbital shape, which is an ellipse. However, these approximations were not as accurate as we expected, since the number of iterations was not close enough to the order of the time interval. The result we were expecting was to achieve a horizontal ellipse, and the graphs we first obtained were tilted and off-center in relation to the origin. It's also worth noting that when the Earth's mass is increased 1/3 of its original mass, its orbit will still follow Kepler's laws. But when increased to half the mass of the Sun, the graph can and will turn into an almost straight line, with only a very small curvature at the beginning of its movement. This last approximation could mean that the orbit collapsed, or that the planet's orbit was completely changed. Kepler's contributions to the field of astronomy and planetary orbits have reached very well beyond their original period. Without Kepler's laws of planetary motion, Isaac Newton might not have been able to come to his conclusion on the law of gravitation.